All right, thermodynamics. We started thermodynamics in the Physics 151, and now we get to look at some calculus aspects. Now, believe it or not, thermodynamics is really heavily mathematical. First of all, sometimes instead of calling it thermodynamics, we simply call it statistical physics. Because everything we're doing is based on statistical calculations. You have billions upon billions of molecules, each molecule having 3 spatial coordinates, x, y, z, and 3 momentum coordinates. And you're trying to calculate what those things are going to do. In a deterministic world, which up to this point you should believe, even though as physicists we don't believe it's a deterministic world. Deterministic world means that if A happens, then B has to happen. So that means that if I push Nathan, he's going to respond with an acceleration. That's deterministic. Quantum mechanics says that it's probabilistic rather than deterministic. But this stuff was all developed back when scientists all believed everything was deterministic. And to all intents and purposes, for our case, it's going to be deterministic. But there's just too many particles to do the calculations to know what each particle is going to do. If you had the computing power, you could calculate what every molecule in this room is going to do from now for all time. But that kind of computing power doesn't exist. So what we have to do is statistical calculations on what's likely to happen. So thermodynamics is based on statistics. And built into that statistics, you have a lot of things like sum from n equals 1 to infinity of this stuff. But you also have some calculus, a lot of calculus. So we're going to look at some of the beginning calculus stuff in thermodynamics. I forgot. I can't do that, Dave. I made a new page instead of moving forward because of a different program. By the way, I believe it was yesterday or the day before the guy who said, I can't do that, Dave, died. Who is not Stan Lee, in case you think I'm getting 2 people confused. Anybody besides Nathan know what I'm talking about? Okay. Well, Stan Lee had nothing to do with it. He also died yesterday. But it's, what's the name of the movie, Nate? 2001 Space Odyssey. The computer tells Dave, I can't do that. Hey. It's a... In my household, we watched that movie because somebody said, this is one of the highest rated movies. We should watch it. It's highest rated because of a bunch of people who like to drop acid and watch it. It goes for like a half hour before you have the first word spoken. It's just bizarre scenes. It's really, we did not enjoy it. So let's get started with this stuff. We've already gone through the Maxwell-Boltzmann distribution. I just included that because that's really a good beginning point to talking about the statistical nature of thermodynamics. But here's our first actual stuff. The first law of thermodynamics. Energy cannot be created or destroyed. We usually write that for a Physics 151 level as the change in internal energy, delta U, is equal to Q, the heat added, minus W, the work done by the system. And so I have the definitions here. U is internal energy, Q is heat added to the system, W is work done by the system. And then I put entropy, S. In entropy, at this point, we will say the change in entropy is equal to heat over temperature. Now, you notice I wrote this in a calculus form, but that D with the Q is messed up. And that's messed up intentionally. Intentionally because Q, heat added to a system, that is a transport. That is a change in energy. Right? So I had delta U is equal to Q minus W. Delta, change in internal energy, equals Q, which is a amount of energy added, minus W, an amount of energy taken away. And so in equations, I'm going to replace Q with a dQ. which sounds really wrong. You know, if you talk about my bank account, I'm going to replace my balance with the change in balance. It doesn't make sense. That's why it's got the line through. It's kind of improper. Because Q is already really a change. So this equation, I mean, for our calculational purposes, we're just going to put ds is equal to dq over t. But that slash through the d is there to remind you occasionally that it's not a normal d because q is really a change. So these are starting points. This equation here then, in calculus form, would be written as du equals d with the slash through at q minus d with the slash through at w. Now we've just been writing w without a slash all this time. But here just pointing out that work is the same thing. Work is an energy change rather than an energy something has. So let's get down to doing something. For mechanics, we knew that work was integral of force dot dx. And so we called this thing here dw. Now we probably should be more accurate and say d slash w, even though I'm going to stop writing slashes right now. So I'm just going to put dw from now on. But in thermodynamics, the force that a gas will apply on a surface is force is equal to pressure times area. And it's going to be in the direction into the surface. So if I have expansion, I will be able to replace f dot dx with pa times dx. Times dx because the area, well, the force is in the same direction or the opposite direction of the change in position. And then we identify that a dx is dv. And so we just have work is integral of pressure dv. I mentioned that in class yesterday. So now we're going to use this. Well, not exactly. The isochoric process. Isochoric, we learned yesterday, isochoric means constant volume. So if I'm going to calculate the work in that case, integral of P dV from V0 to V0. Right, that would be the absolute definition. But why is it silly to write that? Because that'd be zero, because we're starting and ending limits are the same. So it doesn't matter what you get for the integrand, you put in your limits and you're going to get zero. So the work is zero for an isochoric process. Don't need any calculus to do that. We want to calculate the work, the heat, and the change in internal energy between processes. That's really our goal here, to figure out how those things are going to change in a process. So we define this CV such that for anyone watching on the video, that was silence because I was concentrating so hard to make sure I got the words written down right. C sub V is the constant volume. The subscript V means the volume is held constant. Molar heat capacity. Molar heat capacity means heat per mole change in temperature. What we learned before, the specific heat capacity was heat per kilogram change in temperature. So the molar is telling us it's per mole rather than per kilogram. So there's a relationship to relate temperature with heat if you have a constant volume. Q is equal to NCV dt. Now let's look at this from another point of view. If I have a monatomic ideal gas, monatomic, we know that the internal energy is equal to 3/2 nRT, right? So that means du is equal to 3/2 nR dt, right? Right? Okay, Nathan agrees with me. I was hoping somebody would agree with me. Now, if we look at the first law of thermodynamics, du is dq minus dw. Here I put everything in just normal derivatives. And if it's isochoric, which is the case I'm looking at, dw is 0, right? You're not going to have any work. And so I'm going to have 3/2 nR dt is equal to NCV dt. And you get right away, 3/2 nR must be equal to NCV. I'm going to actually put 3/2 R times NDT equals CV times NDT. So we must have CV is equal to 3/2 R. We worked that out in class on Friday. This is just showing it again. So CV is very simple for a monatomic ideal gas. What if it was a diatomic ideal gas? How would things be different if it was a diatomic ideal gas?
Well, we wouldn't have okay, so that one thing
Means 2 atoms instead of 1 per molecule.
then we'll have more degrees of freedom.
Then you'd have more degrees of freedom depending on the temperature. So at really low temperatures, it'd be the same. At room temperature, that goes from 3/2 nRT to 5/2 nRT because we have 2 more degrees of freedom. And if you go to really high temperature, it goes to 7/2 nRT. And so in a general sense, that's a G. U is equal to the number of degrees of freedom times 1/2 nRT. And so, of course, that means du is equal to F over 2 times nRT. And so if we do this, we would find that in general, C sub V is equal to F over 2 times R. Because all I did was I replaced the 3 with F, the number of degrees of freedom. So for any ideal gas, if we know the degrees of freedom, the C sub V is going to be F over 2 times R, where R is the gas constant. So it's easy to calculate Q if you know the beginning and ending temperatures, right? Because you do the integral and you have delta Q, or it's not delta Q, we just put Q again is equal to NCVT, or delta T, as down here. So change internal energy is equal to heat is equal to NCV delta T. For the monatomic, actually it doesn't have to be monatomic in this case because I put CV, for an ideal gas, if it's isochoric. So the isochoric process is the simplest one. W is equal to 0, and delta U and Q are both equal to NCV delta T. Now, if we look at the isobaric process, we define a C subscript P such that the heat is equal to the number of moles times C sub P dt. C subscript P, what does the subscript P indicate? Pressure. Constant pressure. Right, the subscript V, C sub V, it meant constant volume. Here it means constant pressure. So in that case, we're going to have, well, things work out for us to be interesting. If we have an ideal gas, we're still going to have PV equals nRT. And we're going to have U is equal to F over 2 nRT. So that gives us some interesting relationships. Let's look at du is equal to dq minus dw. What is du? Well, du is going to be F over 2 nR dt. dq, what we just did, and C sub p dt. And then dw. Well, dw is, of course, pdv, always. But in the case of isobaric, P is constant, right? And so if I were to do d of PV, that's always going to be P dV plus V dP. But for the isobaric case, because P is constant, that one is 0. So d work is this, which is dPV. Well, why did I do that? Because PV equals nRT. So d parentheses PV is equal to d parentheses nRT is equal to nR dt. So for an isobaric process, this is only true for an isobaric process, what I've just written. But for that isobaric process, then I can replace dW with nR dt. So now I can solve for C subscript P. If I take this, of course, everything has a dt. I'll move this to this side of the equation, and I have F over 2R plus R times n dt is equal to C sub P times n dt. So reading this, the things in parentheses must be correct. C sub P is F over 2R plus R. Well, we had up above that C sub V was F over 2R. So C sub P is C sub V plus R. It's a simple relationship for an ideal gas between the constant volume, molar specific heat, and the constant pressure, molar specific heat. We haven't really done any calculus per se. We've used calculus notation, but we haven't done any integrals or derivatives really yet. So we got a lot more work to do here on the calculus side. But what we've established is that C sub P is C sub V plus R. And up here we had established that C sub V was equal to F over 2 times R. Now, we still want to be able to calculate things like the work. Work is simple. Integral of P dV, if P is constant, is just P times change in volume. So the work for isobaric, very simple. The heat for the isobaric, we have this relationship with temperature, that heat is equal to NCP times change in temperature. Why do I have this written as it is? Because for constant pressure, P delta V is equal to NR delta T. So I just substitute that in. So we have now equations for the work. Either one of these will suffice for the work and for the heat. I was going to say finally, but not even close. Just now we get to the fun stuff. Isothermal. Isothermal, constant temperature. We do not have an equation that says Q equals some constant times change in temperature for isothermal. For a very obvious reason when you think about it. Why don't we have an equation like we had for P and V that says Q is equal to NC sub T dt, or dQ is equal to NC sub T dt? Why does that equation not exist?
Because the change in temperature is 0.
Yes, because the change in temperature is 0. Why would you write such a silly equation? It wouldn't make any sense. So we don't have a simple calculation for heat like we did for the other ones. So instead, we're going to have to work our way around this. So if it's isothermal, since U is equal to F over 2 nRT, if it's isothermal, U doesn't change. U is constant because the temperature is constant for an ideal gas. And so that means delta U is going to be 0. So I have Q minus W equals 0, therefore Q is equal to W. So if I can calculate the work, I know what the heat is for an isothermal process. So the work is equal to the integral of P dV. And I'm saying, like, well, what do I do here? I can't take just an integral of P dV because P is not constant. So I need to put P in terms of V so I can do the integral. Well, what relationship do I have that would relate pressure with volume? Ideally. The ideal gas law, right. So I can take the ideal gas law, PV equals nRT, and solve that for P is equal to nRT over V. Since this is isothermal, T is a constant, so the only variable in there is V. And so I have Q equals work equals the integral of nRT dV over V. That's not hard. What's the integral of dV over V? Okay, maybe it is hard. It's not V. If you were to use the normal power law, you would raise the power by 1 and you'd go from -1 to 0, and that fails us. And so we have a secondary rule in this special case that's natural log. And then you put the limits of V final over V initial. So now we have an equation that says the work equals the heat equals nRT natural log of V final over V initial. So that's going to work for any isothermal process. This was one of the equations that I just gave you guys yesterday and said you got to take it on faith unless you come to class on Tuesday. So now you can see it's not a hard derivation. It's pretty simple calculus, but you have to start putting the ideas together. So now let's go. What's our last process, our last thermodynamic process we've been studying going to be? We've done isochoric, isobaric, isothermal, adiabatic. And what does adiabatic mean? Instead of iso,
Something to do with heat.
yeah, the A is meaning no. No heat. So for an adiabatic process, Q, the heat, is equal to 0. And so du equals 0 minus dw is the first law now. Change in internal energy is minus the work. Well, the change in internal energy is once again going to be what we've been using all along. Not N, F. Got to put a dt here and a dpv. Well, what should dpv equal? Calculus, if I have two things multiplied by each other and I want to find the derivative, what rule do I have to use? The product rule. Multiplication, that's the same thing. And so that's going to be equal to P dV plus V dP. So putting that all together, I have du is equal to F over 2 times P dV plus V dP. But that's equal to minus dW. And dW is P dV. Yeah. Just making sure I copied right. Can we solve this? Let me write down, separating out F over 2 P dV plus F over 2 V dP equals negative P dV. Can I solve this to find anything useful at all? Rhetorical question, the answer is yes. Although we don't know yet how it's going to be useful. What variables do I have in this equation? V, that's one. And P, that's the other. F is a constant, that's the degrees of freedom for my system. So F is a constant here, but I've got the P and V. So what do I have to do if I'm going to solve for V as a function of P or P as a function of V? Go back to the first lecture. The first Tuesday of the semester. Remember, we had things like x equals dv dt. We put in a function for x, and then what did we do? Or v equals dx dt. Wow, I said that wrong. V equals dx dt, and then we put a function for v, and then what did we do? We separated variables. So we got all of the x's on one side and all of the t's on the other. So we have the same calculus situation here. So I'm going to separate variables. The first thing I'm going to do is get my dv's together. So here's a dv, here's a dv. So let me move that across. So I'll add p dv to both sides. And I'm going to subtract f over 2 v dp from both sides. So I now have p dv multiplied by f over 2 plus 1 equals minus f over 2 v dp. It's not separated yet, but it's closer. What's my last step to separating these things? How do we get p's on one side and v's on the other? I didn't hear a clear answer.
Do some algebra.
Do some algebra. Well, that helps. What algebra?
Divide P on both sides. If you
I also need to divide V so that I'll cancel that P and cancel that V. And so I have now to make my life easier, I'm also going to divide both sides by minus F over 2. So that I'm going to have that relationship. Once we've separated variables, what was the next and final step? Separate variables and 3 syllables. Integrate. So now I integrate each side independently from initial to final. We just did this. What's the integral of dv over v? Natural log of v. And so if it's dp over p, we're going to have the same thing. So this is going to be equal to whoops. And now we use our creativity just a little bit. Let's keep things the way they are. If we take this, I can take this and make it the power here. And now since I have a natural log on both sides, the arguments of the natural logs are going to have to be equal. So I won't. I was going to say having the power of erasure, I was just going to erase the ln's. What we do here is we cross multiply. So we have finals on one side and initials on the other. I said cross multiply. It really is, because if I have v sub f raised to a negative exponent, if I multiply it by the same thing with the positive exponent, it'll cancel. So what I have is missed. All of that work to get this relationship between pressure and volume. Now I went from initial to final, but what this indicates is for any adiabatic process, I'm going to have PV to the gamma equals P aught V aught to the gamma is equal to P final V final to the gamma equals constant, where gamma is defined as 1 plus 2 over F, which is equal to C sub P over C sub V. Now, I didn't show you going CP and CV. Let's just show real quickly. C sub P was equal to C sub V plus R, and C sub V was equal to F over 2R. And so if I put this into the relationship, I would have C sub P over C sub V is equal to C sub V plus R over C sub V is equal to 1 plus R over C sub V. The R's will cancel. And so there's the calculation that shows indeed 1 plus 2 over F is C sub P over C sub V. And so we call that, like I said, gamma. All of that work just to find this relationship. Well, why did I do all of that work? Okay, you could just say, well, you said it's just to find this relationship. Why is this relationship important to me? I have no idea. Is that what you're thinking?
It was useful in real life situations.
It's useful in real life situations because it allows us to calculate the work. Because we have the work is integral of P dV. Here we have a relationship between P and V, so I can do that integral. So now that I have this, let's do the work. So taking this relationship right here, I can say P is equal to P initial, V initial to the gamma over V to the gamma, right? That's just dividing both sides by V to the gamma. So I put that in. I do that integral. Well, now it's not dV over V, it's dV over V to the gamma. Assuming gamma is not equal to 1, then we use our normal rule for power integrals. So what's the integral of dV over V to the gamma? I'll put the constants out here. What do you do to the power?
You're doing an integral.
Yeah, doing an integral. You go minus gamma to minus gamma plus 1. You raise it by 1. Or, as we will write this, 1 over V to the 1 minus, or to the gamma minus 1 on bottom. That's raising the power by 1. If gamma had been 2, now it would be to the, instead of 1 over V squared, it's 1 over V, so it's raised by 1.
So, and then do we have to times it by?
Yes, we do. Thank you. I forgot that. In my preparation work, I didn't forget, if that helps. Thank you, Nate. We have to divide by the new power. Well, the new power is gamma minus 1, right? Not V infinity, V final. So if we put in our limits now, You'll actually find some books that leave it something like this. But I prefer to write it in a simpler format, because if I expand this out, it actually becomes kind of simple. What's V0 to the gamma divided by V0 to the gamma minus 1? For instance, if it's V0 to the 5th divided by V0 to the 4th, what would that be?
Zero.
It'd just be V0. You take the exponent, gamma, subtract the 1 on bottom, so gamma minus parentheses gamma minus 1 is just 1. And since P0 V0 is the same as, or P0 V0 to the gamma is equal to PF VF to the gamma, I made this substitution here. And now we can cancel away. I wanted to change the color. There we go. And I'm left with that actually turns out to be a pretty simple equation. It's the product of the final volume and pressure minus the product of the initial volume pressure divided by gamma minus 1. So the calculation, not difficult. We can do that. And I trust I made no sign errors in all of that work. I know it's correct, except for I didn't pay attention to, did I get my signs right? Excuse me. As you know, we can all make sign mistakes. So I'm not going to verify or say I didn't make a sign error there. I don't think I did, but just want to make sure I leave open. So what do we have now? We have a calculation for work for the adiabatic process. And the internal energy change will be the same. Now, the internal energy change will also still be F over 2 NR delta T. But now we have a calculation to make so we can calculate the work independently. Yes, and that was the end of my lecture. Whew. Let me do one more thing since I have 5 minutes left. I had an equation that I introduced in like the second slide that said ds is equal to dq over t. Now that we've gone through and we've calculated how we get q, we can do these calculations as well. If we have dq as a function of temperature, or if we can put temperature as a function of whatever dq is in, then we can calculate the change in entropy. So let's consider the different cases. In the isochoric case, we had dq was equal to n c sub v dt. So what is ds equal to? I'm just asking for a substitution here. So if we integrate both sides, we'll find delta S, the S initial minus S final, is equal to NC sub V, and then what's the integral of dt over T?
I said delta S.
I said delta S, yes. You want S final minus S initial? Because that's also correct.
But wasn't ds the change in S?
ds is an infinitesimal change. Delta S is a finite change. So when I do the integral from S initial to S final, integral of ds from S initial to S final becomes delta S, which is S final minus S initial. The nomenclature is, it's an important aspect, and you're thinking about it, which is good. So there we've done the isochoric case. Isobaric. Isobaric, we had dq was equal to nc sub p dt. So what am I going to have for delta S here? By direct comparison, CP. Wow, those changes in entropy turned out to be really simple for the isochoric and the isobaric. Let's go to isothermal. I don't know how I missed my color. The first one was isochoric.
Is that the one where temperature is constant?
Isothermal is where temperature is constant. What's dq for the isothermal case?
Zero.
It's not zero. Isothermal means that the temperature doesn't change, not that the heat is zero. That's one of the things that we all get confused. So isothermal means the temperature is remaining constant. Let's go back to the isothermal one and see what we had found there. So for isothermal, we had dq was equal to nRT dV over V. Well, I can do that, or I can say that since delta U is 0, Q is equal to minus work. Let's just do that. dq is equal to, I want to use the same thing, so I'm coming back up again because I didn't remember. nRT dV over V. So that means that ds is equal to nRT dV over V divided by T. Well, the T's are going to cancel now. So ds is nR dV over V, which means that delta S is equal to now we can use the ideal gas law to convert from V to other variables, using V is equal to nRT over P, and get it in terms of whatever variable we want. But that's a little bit different. It's fairly similar. Remember, CP is going to be some factor of R as well. And then the final case, adiabatic. What is dq for adiabatic? This one does not require strong memory. Adiabatic means, so dq is 0. So what does that mean for the change in entropy? 0. So adiabatic is also called isentropic, meaning there's no change in entropy either. So we've gone one step further and we've calculated the change in entropy for each one of these steps or processes. All right, our time is done. I'll see you in an hour and a half, right?